Chapter 3 talks about describing relationships between two variables, with the main graph being the scatter plot, and really a focus on linear correlation. Correlation is a term that's only used when we're talking about lines, otherwise it's a. These are the key things we're going to be doing. I'm going to knock out all of 3.1 in this particular lecture, so pay attention, and we'll do quite a bit in class to clarify. First thing we need to talk about, if we are creating a analysis of a two variable situation, is we're going to be looking at creating scatter plots, right? We need to understand the difference between explanatory variables and response variables. Sometimes there really is no clear indication about which thing we think is going to cause the other one. But if it does make sense that one might create or change the other, the explanatory variable is always going to be on the x-axis, and the response, the thing that is the outcome, will always be on the y-axis. One of the things that we want to be really careful from the get-go is correlation or association does not imply causation. The only time we can ever imply that there might be one thing causing the other is in a well-designed experimental situation, which we will talk a lot about in the next chapter. But remember, just because there's an association does not mean that one causes the other. For example, if I measured your hand span and your height accurately, it would be almost a perfect correlation. Ice cream sales and the number of pool drownings. Ice cream sales don't cause people to drown, but there are going to be a higher set of ice cream sales in every summer, and of course there's going to be more drownings in pools in the summer. So there's going to be an association there, but there's no causation. Sodium and fat, there tends to be an increase in the amount of salt that's used when there's more fat, but one does not cause the other. And then there's clearly there's been an increase in AP calculus exams in the last 20 or 30 years, as well as an increase in the average global temperatures, but there's no causation implied there. So we got to be really careful not to include an implication of causation when two things are related to one another. I don't need to talk over this, but you guys need to remember that the explanatory variable goes on the x. Make sure you label and scale your axis, make sure you plot the individual data values, and then we're going to interpret those. Pause this if you need to read it. And you're going to go ahead and read this too. It's kind of funny. When we describe scatter plots, we're going to be looking at a couple of different things. Just like when we were describing one variable data and we paid attention to the spread and the center and the shape and the outliers, we're going to pay attention to the direction, whether it's heading up or down, whether it's going to be a linear or a curve, and then how close together are the dots in that pattern. So if they're really close to a line, it's a strong. If they're farther apart from one another, it's more of a medium or a weak relationship, if any. And then, of course, if they're just all over the place, then there's no relationship at all. We are going to pay very careful attention to outliers in this unit, because outliers can, one or two data points that are outside of the rest of the distribution of the scatter plot can radically affect the correlation strength and direction. So we're going to pay very careful attention to those with different ways of measuring that shift. Positive association means as one thing gets bigger, the other gets bigger. Negative association means as one thing gets bigger, the other gets smaller. And you're going to see an upward trajectory of the points, whether it's linear or curved, and a downward trajectory of points if there's negative association. This one, for example, shows a negative association between the percent of students taking the SAT and the overall score. The fewer number of students who take it, there's going to be an overall higher mean score. The more people that take it, there's going to be an overall lower mean score, but it's not in a linear fashion, it's more curved. There seem to be two distinct clusters from a small population to a large population. before I read it, and you can read it yourself, you can go ahead and describe how you would do this. You can just stop it and check yourself. But this is a looking at points per game and how that relates to the wins. And if you'd imagine there would be a positive correlation. More points, better chance of winning. So there's a positive association for sure. It does seem to be linear instead of curved, so we can start talking about correlation. And we're going to talk about how we can calculate the strength of that when it seems linear. Pretty strong. And there are no outliers on this particular thing. So we can say that there's a relationship, a positive relationship between points per game and wins. And since it's linear, we can start talking about the correlation coefficient. Statisticians not big fans of things like it's moderately strong or super strong just by eyeballs. We have a way of calculating a correlation. We only calculate correlation R when it's a linear function. It talks about how strong of a linear relationship it is. Just because the correlation coefficient might be high doesn't mean that a linear function, linear model is actually appropriate. And we're at the end of the chapter. We're going to look at that again, the same way we looked at whether a normal curve would be an appropriate model for a set of data. But if we decide that it's linear, then we can look at correlation R to quantify how strong it is. So R is always a number between 1 and -1. And stuff over here indicates a positive association, and stuff down here indicates a negative association. And the stuff in between means not really much. So values near 0, weak linear relationship, if any. And the strength of a linear relationship is the closer you get to 1, super strong, closer you get to -1, super strong. And the only time you're ever really going to get an exact -1 or an exact +1 is when you have an exact line. And that really doesn't happen very often in real data sets. But if you can get a 0.9 or 0.99, that's really strong. And there's definitely seems to be an association between those. So here are some examples, and there are correlation coefficients. You'll notice this one's all over the place, and the correlation is 0. This one tends to have a downward facing slope, and it has an R correlation of -0.3, not super strong. And this one is positive at about 0.5. You'll notice, as they get closer together, the dots get closer together, the correlation gets stronger, whether it's heading in a negative direction or a positive direction. The tighter the data points are, the closer that number is to positive or -1. Here, my friends, is the correlation coefficient formula, and we will never have to calculate it by hand. You might have to calculate it on the calculator, but most of the time we're going to give it to you, and we'll practice it a little bit. But basically, all we're doing is we're taking the z-score of each xy point, the z-score of each x point, and the z-score of each y point, multiplying it together, and then we're going to divide that by the number of data items -1. Yeah, we're not going to calculate that by hand. So correlation, it's really important that you have some certain distinctions. R correlation doesn't make a distinction whether you've got the explanatory response variable which place. It's going to work out that if it's a negative correlation, the x and the y can flip, it's still going to be a negative correlation. R does not change when we change the units or the measurement of x and y or both. It's still going to stay the same strength. So if we went and took the temperature and someone's body temperature and we changed it from Celsius to Fahrenheit, it wouldn't change the shape of the correlation or the strength of R. And the correlation R itself has no unit of measurement, so it's just a number that indicates between -1 and +1 how strong of a correlation and in what direction. Super important here. We don't even use the word correlation unless we're talking about a linear relationship. If it's a curved relationship, and they do exist, we'll focus on them later in the year, then we can find some ways of measuring how strong it is, but we will never use the term correlation or R correlation coefficient to help us to understand how strong a curve relationship is at all. Obviously, both variables need to be quantitative. Correlation is highly, highly, highly affected by outliers, and we're going to look at two different simulators in the next couple of days to help us see how quickly the correlation can change from strong to weak to flipped, so positive to a negative correlation with just one or two outliers. And correlation is not a complete summary of two variable data. We're going to look at R squared, we're going to look at S, we're going to look at all sorts of other things later that can help us to understand. A reminder, this is what you're being asked to understand from 3.1, and make sure after you've done the Google form quiz that you come in with any questions that you might have.